By 2005, the Voyagers had reached the termination shock, where the solar wind slows and becomes turbulent as it mixes with the interstellar medium, entering the heliosheath region. By 2016, they were nearing the heliopause, where the solar wind is stopped by the interstellar medium. Charles Kohlhase. Charlie Kohlhase was born in Knoxville, Tennessee, and graduated with a degree in physics. He briefly served in the U.S. Navy before joining JPL in 1960, where he turned his lifelong fascination with exploration into work on the Mariner and Viking projects, before joining the Voyager team. In 1997, Kohlhase left Voyager to design the Cassini-Huygens mission to Saturn, which succeeded in dropping a lander onto the surface of Titan in 2005. In the late 1970s, he worked with computer artists to create accurate animations of space missions for advancing the public understanding of NASA's work. Now retired, Kohlhase remains involved in several projects that blend art and space science, aiming to educate and inspire the next generation of rocket scientists and interplanetary explorers. Key work: 1989 The Voyager Neptune Travel Guide. See also, Life on Other Planets, The Nebular Hypothesis, Exoplanets, Understanding Comets, Studying Pluto. In context: Key astronomer Vera Rubin. Before 1925 Bertil Lindblad calculates the likely shape of the Milky Way. 1932 Jan Oort finds that the rotational speeds of the Milky Way galaxy do not match the presumed mass. 1933 Fritz Zwicky suggests that a majority of the universe is made up of dark, invisible matter. After 1999 it is discovered that dark energy is accelerating the expansion of the universe. 2016 The LIGO experiment detects gravitational waves, which offer a new method to map the distribution of dark matter across the universe. Isaac Newton's universal law of gravitation is adequate for making calculations to launch a satellite into orbit, land a crew on the moon, and send a spacecraft on a grand tour of the planets. Newton's clear mathematics works well enough for most things on the solar system scale, but not on grander scales of the universe, where Einstein's relativistic theory of gravity is needed. Nevertheless, Newton's law of gravitation was all that was required to reveal one of the biggest, and as yet unsolved, mysteries of astronomy: dark matter. In 1980, American astronomer Vera Rubin presented clear evidence that dark matter exists. Thanks to Rubin, the general public learned that most of the universe appears to be missing. Throughout the 1960s and 1970s, the science of astronomy was dominated by projects on a grand scale, as researchers used massive instruments, often in remote parts of the world, to search for exotic objects, such as black holes, pulsars, or quasars. By contrast, Rubin was looking for a research area that would allow her to stay in her home city of Washington, D.C., and raise her 4 children. She chose to study the rotation of galaxies, specifically looking at the anomalous behavior of the outer regions of galaxies. We became astronomers thinking we were studying the universe, and now we learn that we are just studying the 5% that is luminous. Vera Rubin. Spinning spirals. The problem Rubin tackled was the fact that huge disks of stars in nearby galaxies did not move in a way that was consistent with Newton's law of gravity. Their outer regions moved too quickly. This curiosity was not new, but it had previously been largely ignored. Since the 1920s, when Bertil Lindblad and others showed that the Milky Way, and by extension many other galaxies, were disks of stars moving around a central point, it was assumed that galaxies were orbital systems just like any other. In the solar system, near objects orbit at a faster speed than distant ones, so Mercury is moving much more rapidly than Neptune. This is because, following Newton, gravity decreases with the square of the distance. When the velocities of the planets are plotted against their distance from the Sun, the data forms a smooth downward rotation curve. It followed that plotting the orbital speeds of stars at different distances from the galactic center should produce a similar curve. In 1932, Dutch astronomer Jan Oort was the first person to provide observational proof that the galaxy was a single orbital system made up of a swirling spiral of stars, in which the Sun completed a 225 million-year orbit. However, in the course of his calculations, Oort found that the motion of the galaxy suggested that it was twice as massive as the total mass of visible stars. He concluded that there must be some hidden source of mass. A year later, the Swiss-American Fritz Zwicky was studying the relative motion of galaxies in the Coma cluster. He found again that their motion suggested the mass of what could be seen was not the only stuff there. He named the missing material Dunkel Materie, or dark matter. Oort's early measurements were inaccurate, while Zwicky's initial assessment was that dark matter was 400 times more abundant than the matter of visible material, a huge overestimate. This meant that their findings were dismissed as measurement errors. In 1939, American Horace Babcock again found anomalies in the rotation of Andromeda and suggested that there was some mechanism by which light from the missing matter was being absorbed in the galactic core. Galactic rotation curve. More than 20 years later, Rubin returned to the problem of galactic rotation. Like Babcock, she chose to focus on the rotation of the Andromeda Galaxy, the Milky Way's nearest galactic neighbor. She worked with her colleague Kent Ford at the Carnegie Institution of Washington to measure the velocities of objects in the outer region of the galaxy. They did this using a sensitive spectrograph, which allowed them to detect the redshift and blueshift of objects, and calculate their relative speeds away from and toward Earth. After several years of slow but careful work, Rubin had enough data to plot a rotation curve for the galaxy. Instead of swooping downward like the curve of the solar system, the speed data of the galactic curve stayed relatively level with distance. This meant that the outer regions of Andromeda were moving at the same speed as the areas nearer to the center. If the galaxy's mass was limited to what could be observed using telescopes, the outer regions of Andromeda would be moving faster than escape velocity, and they should simply fly off into space. However, they were clearly being held in place by the galaxy's overall mass. Rubin calculated that the total galactic mass required to hold the outer regions in orbit was about 7 times greater than the visible mass. The ratio of matter to dark matter is today thought to be around 1:6. In the absence of dark matter, the velocities of objects in the outer regions of galaxies would be slower than the observed values. Here, the observed rotation curve is plotted against the expected curve from visible matter alone. What is dark matter? Rubin's galactic rotation curve, widely disseminated in 1980, was the visual proof that dark matter existed. As further evidence mounted, the mystery as to what it might be remained. Dark matter cannot directly be observed, only its effects are detectable, and the only effects that can be detected are from its gravity. It does not interact with the electromagnetic force, meaning that it does not absorb heat, light, or other radiation, nor does it emit any. Dark matter may be completely invisible. No observational problem will not be solved by more data. Vera Rubin. Dark matter could be evidence that the universe is one of many that exist next to one another, in separate spatial dimensions, in a bubble-like multiverse. Possible sources. The simplest solution to the dark matter problem is the most literal. It comprises ultra-dense bodies of ordinary matter that are too dark to observe. Astronomers have dubbed these machos, which stands for massive compact halo objects. Machos include objects like black holes, neutron stars, and white and brown dwarfs. They occupy the galactic halo, a dark and diffuse region that surrounds the main, shining disk of a galaxy, and this is why it is difficult to see them. Machos are clearly out there, but by current estimates they would only account for a tiny proportion of dark matter. An alternative idea is the WIMP, weakly interacting massive particle. This concept is based largely on an idea in particle physics called supersymmetry. It proposes a new explanation of energy and ordinary matter. Energy and matter form two distinct groups of subatomic particles, and supersymmetry proposes that these groups interact thanks to the actions of superparticles, or sparticles. Dark matter WIMPs might be sparticles that escaped from their partners in the early period of the universe, or they may be objects that are there all along. Finally, dark matter might be the observable effect of another universe, or perhaps several, that exist in a spatial dimension different from this universe. Their matter could be very close, a few centimeters away, but because the radiation from each universe is trapped inside its own spacetime, one universe can never see another. However, the gravitational effects of the matter in the hidden universes leaks through into this one through the warping of spacetime. Providing an explanation for dark matter remains one of the biggest prizes in astronomy. However, in 1999, a possibly even more puzzling phenomenon was uncovered. It was discovered that 68% of the universe was neither matter nor dark matter, but so-called dark energy. Dark matter makes up 27%, visible matter comprises a mere 5%. For the moment we might very well call them dinos. Bill Bryson. A huge ring of dark matter, which formed long ago in the collision between two massive galaxy clusters, is shown around the edge of this Hubble Space Telescope image in lighter blue. Vera Rubin. Born Vera Cooper in Philadelphia, Rubin earned her first degree from Vassar College in upstate New York, and then applied to go to Princeton. Her application was ignored because women were barred from joining the university's graduate astronomy program until 1975. Instead, Rubin pursued her studies at Cornell University, where she studied under greats such as Richard Feynman and Hans Bethe. She subsequently earned a Ph.D. from Georgetown University in Washington, D.C., supervised by George Gamow. Her thesis, published in 1954, concluded that galaxies would clump together, a fact that was not fully explored until the work of John Huckra in the late 1970s. After teaching at a college in Maryland, Rubin returned to Georgetown, and then moved to the Carnegie Institution of Washington in 1965. It was here that she conducted her work on galactic rotation, and she has remained there ever since. Key work. 1997 Bright Galaxies, Dark Matters. See also, Gravitational Theory. Gravitational disturbances. The shape of the Milky Way supernovae. The Oort cloud. Dark energy. In context. Key astronomer Alan Guss. Before 1927, Georges Lemaitre proposes that the universe arose from a single primordial atom. This is later named the Big Bang Theory. 1947, George Gamow and Ralph Alford describe how the elements hydrogen and helium were formed in the early universe. 1964, the cosmic microwave background is discovered to be a remnant of the Big Bang. After 1999, dark energy is found to be accelerating the expansion of the universe. 2014, Bicep 2 withdraws claims of finding evidence of inflation. 2016, LIGO detects gravitational waves, offering a new way to observe the structure of spacetime. By the 1970s, cosmologists were grappling with a variety of puzzles thrown up by the Big Bang Theory. In an attempt to solve them, Alan Guss proposed a stage of rapid inflation in the early universe, caused by the effects predicted by quantum theory. The puzzles. One of the problems with the Big Bang Theory came from the Grand Unified Theory, which describes how the forces of the universe arose a fraction of a second after the Big Bang. The GET predicted that high temperatures at this time would create bizarre features, such as so-called magnetic monopoles. There are, however, none to be found, which suggests the universe cooled faster than expected. A second problem arose from the way space is amazingly flat, meaning that it expands according to normal Euclidean geometry. A flat universe would only have arisen if the density of the early universe matched a certain critical figure. Varying it slightly one way or the other would have resulted in curved universes. The final issue was the horizon problem. Light from the edge of the observable universe has taken the entire life of the universe to reach Earth. As light's speed is constant, scientists know that it has not had time to shine to the opposite edge of the universe. So if no light, energy, or matter has ever passed between the edges of the universe, this leaves a puzzle as to why space appears so similar in every direction. The solution. Goose's theoretical solution to these problems was to inflate the early universe using a quantum effect called a false vacuum, where positive matter energy was created as space expanded, equally balanced by an increase in gravity. In the first 1035 seconds after the Big Bang, space doubled in size 100 times over, going from a billionth of the size of a subatomic particle to the size of a marble. This means that, at the very beginning, the edges were close enough to mix and become uniform, thus solving the horizon problem. During inflation, space expanded faster than the speed of light. The inflation cooled the universe rapidly, thus solving the GUT problem, and locked in the uniformity seen today. Finally, the inflation ended as the density of the universe evened out at a value needed for a flat universe. In 2014, BICEP-2, an experiment at the South Pole, reported ripples in space consistent with cosmic inflation. However, the claim was soon withdrawn. Cosmic inflation remains unproven, but it is the best current theory for the Big Bang. The recent developments in cosmology strongly suggest that the universe may be the ultimate free lunch. Alan Guth. It is not possible to visualize warped three-dimensional space, but if one dimension were removed, the geometry of space could be shown as curved, saddle-shaped, and flat, where a triangle with angles of 180 degrees would be drawn. Alan Guth. Born in New Jersey, Alan Guth received his doctorate in 1972 and specialized in particle physics, pursuing research into quarks. By the late 1970s, he had worked at MIT, Princeton, Columbia, Cornell, and Stanford, as he searched the country for a long-term academic position. While at Columbia, Guth became interested in the grand unified theory, which had been proposed in 1974. He began developing his inflation theory in 1978, while at Cornell, after hearing about the problem of the flatness of the universe, and shortly afterward, the problems associated with GUT. While at Stanford, he then came across the horizon problem, and went on to publish his famous theory in 1981. He is now a professor at MIT, where he helps with the search for evidence of cosmic inflation. Key works: 1997, The Inflationary Universe, The Quest for a New Theory of Cosmic Origins, 2002, Inflation, and a New Era of High-Precision Cosmology. See also, The Birth of the Universe, the Primeval Atom Searching for the Big Bang Gravitational Waves. In context: Key astronomers Margaret Geller, John Huckra. Before 1842, Christian Doppler describes how wavelengths can change due to relative motion. 1912, Vesto Slipher discovers that galaxies are redshifted by the Doppler effect. 1929, Edwin Hubble uses redshift to show that distant galaxies are moving away faster than nearer ones. 1980, Alan Guth proposes that a rapid expansion, called cosmic inflation, shaped the universe. After 1998, the Sloan Digital Sky Survey finds walls, galaxy sheets, and filaments many hundreds of light-years long. 1999, a redshift survey of supernovae reveals that the universe's expansion is speeding up. Since the 1920s, the study of the redshift of distant galaxies has revealed the scale of space and the way in which the universe is expanding in all directions. Redshift occurs when a light source is moving away from the observer. In the 1980s, redshift surveys made by American astronomers Margaret Geller and John Huckra, working at the Harvard-Smithsonian Center for Astrophysics, gave an even clearer picture of the universe, showing that galaxies cluster around great voids of empty space. Geller and Huckra's work provided valuable clues to the nature of the very early universe. A redshift survey uses a wide-angle telescope to select target galaxies, generally millions of light-years away. Astronomers compare the light from each galaxy with benchmark wavelengths to determine the redshift, and thus the distance the light has traveled, allowing them to plot the positions of many galaxies. Huckra started the first redshift survey in 1977. By its completion in 1982, He had mapped 2,200 galaxies. Before Huckra began his survey, it was known that galaxies existed in clusters. For example, the Milky Way is one of at least 54 galaxies in a cluster called the Local Group, which is about 10 million light-years wide. It was assumed that clusters were evenly spread. However, by 1980, Huckra had shown through his redshift survey that dozens of clusters form superclusters hundreds of millions of light-years wide. The Local Group is part of the Laniakea supercluster, which contains 100,000 other galaxies. Walls of galaxies. In 1985, Geller began the CFA2 redshift survey, taking 10 years to map 15,000 galaxies. Her survey confirmed that superclusters were themselves arranged in sheets and walls enclosing vast voids, like the surface film of a bubble. She found the first Great Wall of galactic superclusters in 1989. The exact size of CFA2 Great Wall is still unclear, but it is estimated at 700 million light-years long, 250 million wide, and 16 million thick. It was the first of several supersized structures now known. The size of the voids puzzled astronomers. They were too large to have been emptied completely by the gravitational collapse of material that formed the stars and galaxies, which meant that they must have been empty since the beginning of the universe. Cosmologists theorize that the large-scale order of superclusters and voids is the legacy of quantum fluctuations during the inflationary epoch of the universe. Quantum fluctuations are fleeting changes in the amount of energy at points in space. These small but highly significant irregularities were locked into the fabric of the universe in the first fraction of a second of its existence, and remain today. They are now the vast areas of void permeated by a tangled pattern of matter. This computer simulation of a portion of the universe shows the distribution of 10,000 galaxies, which cluster in long filaments and walls in between vast empty voids. Margaret Geller. Margaret Geller earned a Ph.D. from Princeton in 1975 and took various fellowships before joining the Harvard Smithsonian Center for Astrophysics in 1983. She worked there with John Huckra, analyzing the results of his redshift survey. Geller went on to lead the second redshift survey. She is a frequent public speaker and has made several films about the universe, including Where the Galaxies Are, which takes viewers on a graphical voyage around the large-scale objects of the observed universe. See also, Spiral Galaxies Beyond the Milky Way Cosmic Inflation, a digital view of the skies. In context. Key astronomer Frank Hsu. Before 1947, Bart Bok observes dark nebulae and suggests that they are sites of star formation. 1966, Frank Hsu and Chia Chow Lin developed the density wave theory to explain spiral arms in the Milky Way. After 2003, the Spitzer Space Telescope, an infrared observatory, is launched. It produces the best view yet of stellar nurseries. 2018, first light on the James Webb Space Telescope will allow astronomers to study protostars inside dark Bok globules. Stars form inside dark globules of dust and gas that are called giant molecular clouds. However, the process by which a cloud of gas transforms into an embryonic star, or protostar, has never been observed, partly because the process must take millions of years, and partly because even the most advanced telescopes find it difficult to penetrate the dark density of the cloud. Without observational evidence, astrophysicists must construct mathematical models for what they think is happening inside those dark globules. The most consistent model of star formation was derived by U.S. mathematician Frank Hsu. Hsu and his colleagues Fred Adams and Susana Lozano at the University of California at Berkeley presented their model in 1986 after 20 years of work. The pillars of creation are vast clouds of gas and dust where new stars are made. This famous image was captured by the Hubble Space Telescope in 1995. The inside-out model. Hsu's system is called the singular isothermal model, or the inside-out model. It is built from the complex mathematics that define the dynamics of gas clouds, taking into account factors such as temperature, density, electrical charge, and magnetism. Shu's model works by making the process self-similar. A starting condition that causes some of the gas cloud to contract into a dense core will result in the same, or similar, conditions, which cause more gas to join the core, and so on. This process was found to be stable enough to keep the young star together as it grew. Earlier models had failed because they could not find a way to balance the mechanisms that were pulling the gases in and pushing heat out. As a result, these models ended with the young star disintegrating. GMCs are vast regions of the galaxy filled with hydrogen atoms and molecules mixed with specks of dust and ice. Typically, a GMC contains 100,000 solar masses of material, which is a mixture of primordial gases produced by the Big Bang and the remnants of long-dead stars. GMCs are mostly found in the spiral arms of a galaxy. In the mid-1960s, Shu and the renowned Chinese-American mathematician Chiao Lin modeled the rotation of a spiral galaxy, and showed that the arms are located at density waves, traffic jams, of stars. Such density waves sweep up interstellar material into GMCs, and this triggers the formation of stars. The impact of a density wave, or something more violent such as a blast from a nearby supernova, creates turbulence inside a GMC. However, highly tangled magnetic fields run through the cloud, and these stop the turbulence from ripping the cloud apart. The magnetism also acts to prevent the cloud from collapsing in on itself under its own gravity. Cloud cores. Over millions of years, the magnetic pressure and turbulence in the gases dissipate, creating regions of calm, where slowly rotating cloud cores form. On closer inspection, GMCs are not uniform, but made up of dark fragments or clumps of denser material, known as Bach globules. Each globule is thought to contain several cloud cores. Shu's model supposes that the core becomes a single isothermal sphere, or something very close to it. This means that the gravity pulling the ball of gas together is balanced by the outward pressure of the moving gas and its magnetic forces. Such a state can never persist for long, and the contracting gravitational force in the core wins out over the outward pressure. The inner region of the cloud core contracts to form a dense ball of gas at the center. This is the protostar. Protostars do not form in a rapid process, but take millions of years, and millions more to grow into a full-fledged star. The protostar is also surrounded by a disk of material formed by the system's rotation, and wave upon wave of material is pulled in from the surrounding envelope of gas. With each wave, the mass of the protostar and its more diffuse disk grows, and its gravity grows with it. The increasing gravity steadily pulls in material from farther away, hence the description of the process as an inside-out collapse. Frank Shu's inside-out model describes the four-stage formation of a star from a giant molecular cloud. The star gathers mass. The protostar warms up as it becomes denser, but it is still too small and cold to produce energy by fusing hydrogen in its core. The force of all of the new material landing on its surface also adds to the heat signature given out by the protostar. At this stage, it is giving out only faint infrared and microwave radiation, which makes it hard to see. Eventually, however, the protostar gathers enough mass for fusion to begin, but initially only the deuterium, a heavy isotope of hydrogen, begins to burn. Unlike an adult star, a protostar releases its heat entirely by a process of convection. Heat from its core rises up to the surface in the same way that hot water in a pan rolls around as it boils. The convection and rotation of the star create a strong magnetic field, which pushes out from each pole, clearing a narrow hole in the envelope of gas and dust. The growing protostar's heat and a stellar wind of plasma are directed away from the star via these polar jets. These features, explained by Shu's model, have been confirmed by observations. An infant star sits at the center of two nearly symmetrical jets of dense gas. Known as Karma 7, the star is about 1,400 light-years from Earth. Becoming a star, almost. A star with the mass of the Sun spends about 10 million years as a protostar. As its mass increases, the angle of its polar jets widens, pushing away more of the gas cloud. Eventually, the protostar's stellar wind blasts out from the entire star's surface, and it clears its gas cloud away completely. At this point, the young stellar object is revealed for the first time. Giant stars have already started burning hydrogen by this point, and have become full-fledged stars destined to live short, bright lives. However, smaller stars, those less than 8 solar masses, have not begun a full fusion process, and so are known as pre-main sequence stars. A PMS star still has a disk of material spinning around it. Some of that will be dispersed by the stellar wind into the wider GMC. What remains, around the smaller stars especially, is likely to form into gas giant planets, and perhaps later, rocky ones as well. A protoplanetary disk surrounds the young star HL Tauri in the constellation Taurus. The dark patches are thought to represent the possible positions of newly forming planets. Final ignition. The final phase of star formation is a contraction of the fast-spinning PMS star. Red, orange, and yellow dwarfs form from PMS stars that are less than 2 solar masses. They are considerably wider and less dense than their adult forms, and appear much brighter as they give out light from larger surface areas, frequently punctuated by high-energy outbursts of X-rays. This energy is the product of gravitational contraction, not nuclear fusion. It takes about 100 million years for the PMS star to compress itself enough to begin burning hydrogen, and by that time, it will have lost half to 3/4 of its initial mass. Larger PMS stars take a different route to achieving fusion and form rare blue dwarfs. PMS stars are the earliest stage of star formation that have been seen clearly. Infrared space telescopes such as Spitzer and Hubble have given faint glimpses of protostars, but mostly they are too heavily shrouded by the dark dust clouds. NASA's new Infrared James Webb Space Telescope is designed to be sensitive enough to see through that dust, so perhaps soon the moment when a star is born may at last be observed. Frank Xu. Born in Kunming, China, Frank Xu moved to the United States when he was 6 to join his father, an academic mathematician, who was beginning research at MIT. Frank followed his father to MIT, where he completed a degree in physics in 1963. While there, Xu worked on the density wave theory of spiral arms. He later moved to Harvard to complete his doctorate in astronomy in 1968. Xu worked on his protostar model while at Berkeley and was the head of the astronomy department there by the time he presented the full review of his isothermal sphere model in 1986. Today, Xu holds tenure at Berkeley. In recent years he has used his knowledge of astrophysics to tackle climate change. He often works in collaboration with his graduate students, who are collectively known as the Xu Factory. Key work. 1981 The Physical Universe. See also, Stellar Composition Nuclear Fusion within Stars Energy Generation Dense Molecular Clouds Studying Distant Stars Genes and Bartsumian. In context. Key astronomers George Smoot John Mather before. 1964 The cosmic microwave background, an echo of the Big Bang itself, is discovered. 1981 Alan Guth proposes cosmic inflation, a theory in which fluctuations of energy density were locked into space during the Big Bang. 1983 Redshift surveys show that galaxies are clustered around voids of nothingness. After 2001 Wilkinson Microwave Anisotropy Probe is launched to refine the map of the CMB. 2015 The Planck Observatory studies the CMB to refine the age of the universe to 13.813 billion years plus 38 million years. Combining this with other data, the latest estimate is 13.799 billion years plus 21 million years. The cosmic microwave background, or CMB, was discovered in 1964. This is the afterglow of the Big Bang, and it is as near as scientists can get to observing the event that brought the universe into existence, 13.8 billion years ago. Linking the structures observed in the universe to the features discerned in the CMB remains a key challenge for cosmologists. I always think of spacetime as being the real substance of space, and the galaxies and the stars just like the foam on the ocean. George Smoot. Wrinkled time. The first great breakthrough came from the Cosmic Microwave Background Explorer, known as COBE, a NASA satellite launched in 1989. The detectors on COBE, designed and run by George Smoot, John Mather, and Mike Hauser, were able to find the oldest structures in the visible universe, described by Smoot as wrinkles in time. These wrinkles in otherwise uniform space were once dense regions containing the matter that would form stars and galaxies. They correspond to the large-scale galaxy superclusters and great walls seen in the universe today, and add weight to the inflationary model of the early universe proposed by American Alan Guth. The CMB is a flash of radiation that was released about 380,000 years after the Big Bang, at the time the first atoms formed. The expanding universe had cooled enough for stable ions of hydrogen and helium to form, and then, after a little more cooling, the ions began to collect electrons to make neutral atoms. The removal of free electrons from space led to the release of photons. Those photons are visible now as the CMB. The CMB comes from the whole sky, without exception. It has redshifted, and it now has wavelengths of a few millimeters, while the original radiation's wavelengths would be measured in nanometers. One of the key observations of the CMB came in the 1970s, and removed any doubt that it was an echo of the Big Bang. This was the discovery that the thermal spectrum of radiation from the CMB tallied very closely with that of a theoretical black body. The Cosmic Microwave Background Explorer spent 4 years in space collecting information about the CMB, scanning the celestial sphere every 6 months. Black bodies. Black bodies do not really exist, they cannot be made, and no object observed in the universe functions as black bodies do in theory. However, the CMB is the closest match that has ever been found. A black body absorbs all radiation that hits it. Nothing is reflected. However, the absorbed radiation adds to the thermal energy of the object, and this is released as radiation. In 1900, German Max Planck, the founding figure of quantum physics, showed that the spectrum of radiation released by a black body is entirely dependent on temperature. In an everyday example of radiation varying with temperature, an iron bar glows red when first heated. Heating it more makes it orange, and eventually the bar will glow blue hot. Metalworkers learn to roughly judge the temperature of iron by its color. The metal is not particularly close to a black body in the theoretical sense, but stars and other astronomical objects are a much closer match to a black body, and so the color, or wavelengths of their emissions, can be compared to the thermal spectrum of a theoretical black body to give a relatively precise temperature. The temperature of the CMB today is a chilly 2.7 K. The thermal spectrum at that temperature contains no visible light, which is why space looks black to human eyes. However, the spectrum has redshifted over time as the universe has expanded. Extrapolating back to the moment the CMB was emitted gives an original temperature of about 3000 K. The color of radiation at this temperature is orange, so the CMB started out as a flash of orange light that shone out from every point in space. Smooth signal. The early observations of the CMB suggested that it was isotropic, which means that its spectrum is the same everywhere. In cosmology, the terms density, energy, and temperature are somewhat synonymous when discussing the early universe. So the isotropic nature of the CMB suggested that, in those early days, space had a uniform density, or spread of energy. However, this did not tally with the developing theories of the Big Bang, which demanded that matter and energy were not evenly spread through the young universe, but had been concentrated together in places. These denser areas, or anisotropies, were where the stars and galaxies formed. COBE was sent into space to take a close look at the CMB to see if it could find any anisotropies, to find out whether the CMB changed, however slightly, depending on where it looked. The full sky map produced by WMAP in 2011 showed many fine details of the isotropy of the CMB. Colder spots are blue, while hotter spots are yellow and red. COBE's mission. A mission to study the CMB from space had been in the planning stages since the mid-1970s. Construction of COBE began in 1981. It was initially designed to enter polar orbit. However, the Challenger disaster of 1986 grounded the shuttle fleet, and the COBE team had to look for another launch system. In 1989, the satellite was launched using a Delta rocket, and it was placed in a sun-synchronous geocentric orbit, orbiting in a way that saw it pass over each place on Earth at the same time of day. This worked just as well as a polar orbit in that it allowed COBE to point away from Earth and scan the entire celestial sphere strip by strip. The spacecraft carried 3 instruments, all protected from the sun's heat and light by a cone-shaped shield, and chilled to 2K using 100 gallons of liquid helium. George Smoot ran the differential microwave radiometer, which mapped the precise wavelengths of the CMB, while John Mather was in charge of FARAS, the far-infrared absolute spectrophotometer, which collected data on the spectra of the CMB. These 2 experiments were looking for anisotropies. The third detector on COBE had a slightly different goal. The diffuse infrared background experiment, run by Mike Hauser, found galaxies that were so ancient and far away that they are only visible by their heat radiation. COBE's instruments created the most accurate map of the CMB to date. However, it was not a simple surveying job. Smoot and Mather were interested in primary anisotropies, that is, the density differences that were present at the time the CMB formed. To find these, they needed to filter out the secondary fluctuations caused by obstacles that lay between COBE and the edge of the universe. Dust clouds and the effects of gravity had interfered with the radiation on its long journey to Earth. The data from the 3 instruments were used to detect and correct these so-called secondary anisotropies. The greatest discovery of the century, if not of all time. Stephen Hawking. In addition to mapping the CMB, WMAP measured the age of the universe as 13.77 billion years, dark matter as 24% of the universe, and dark energy as 71.4%. Tiny fluctuations. After 10 months in space, COBE's helium ran out, which limited the function of the 2 infrared detectors, but the DMR continued working until 1993. By 1992, the COBE team's analysis had shown what they were looking for. The CMB, and thus the early universe, was not a uniform blob of energy. Instead, it was riddled with tiny but significant fluctuations. The differences were minute, with density variations of about 0.001%. However, the pattern was enough to explain why the contents of the universe are clustered together, while the rest of space is made from vast empty voids. Since COBE, 2 subsequent missions have added detail to the picture of the CMB. Between 2001 and 2010, NASA's Wilkinson Microwave Anisotropy Probe mapped the CMB to a higher resolution than COBE. Then, from 2009-2013, the ESA's Planck Observatory produced the most accurate map to date. Every wrinkle on the map is the seed from which an entire galaxy formed about 13 billion years ago. However, no known galaxy can be seen forming in the CMB. The CMB radiation detected today has traveled from near the edge of the observable universe over the course of most of the age of the universe. Astronomers can only see 13.8 billion light-years away, but most of the universe now lies farther away than that. The galaxies forming in the CMB are now far beyond what can be observed, and are receding faster than the speed of light. George Smoot. After a childhood in Florida and Ohio, Smoot began his career as a particle physicist working at MIT. His interests switched to cosmology, and he moved across the country to the Lawrence Berkeley National Laboratory. It was there that Smoot studied the CMB and developed ways of measuring its radiation. Smoot's early work involved fitting detectors to high-altitude U-2 spy planes, but in the late 1970s, he became involved in the COBE project to take his detector into space. After his success with COBE, Smoot co-wrote Wrinkles in Time with Key Davidson to explain the discovery. Smoot won the Nobel Prize in 2006, along with John Mather, for his work on COBE. He reportedly gave his prize money to charity. However, 3 years later, Smoot won an even greater sum when he bagged the $1 million jackpot on the TV game show Are You Smarter Than a Fifth Grader? Key work. 1994 Wrinkles in Time. See also, The Birth of the Universe Searching for the Big Bang Cosmic Inflation Redshift Surveys Tegmark. In context. Key astronomers David Jewitt Jane Lu before. 1930 American astronomer Clyde Tombaugh discovers Pluto orbiting beyond Neptune. It is initially identified as the 9th planet, but is later reclassified. 1943 Kenneth Edgeworth suggests that Pluto is just one of many objects in the outer solar system. 1950 Fred Whipple describes the icy nature of comets as dirty snowballs. After 2003 Sedna is discovered orbiting 76,000 Australian dollars AU from the Sun, beyond the outer edge of the Kuiper Belt. 2005 Eris is seen in the disk beyond the Kuiper Belt. 2008 Two Kuiper Belt objects are classified as dwarf planets along with Eris, Pluto, and Ceres. In 1950, Dutch astronomer Jan Oort proposed that a spherical shell of potential comets surrounds the solar system half a light-year away. The so-called Oort cloud was the source of long-period comets, which took millennia to orbit the Sun. But the source of the short-period comets that orbit the Sun every few centuries must be nearer. In 1943, Irish scientist Kenneth Edgeworth speculated that the comet reservoir was a belt beyond Neptune. But the Dutch-American astronomer Gerard Kuiper argued in 1951 that, although there was once such a belt, it would have been scattered away by the gravity of the outer planets. It was a puzzle, and comet nuclei that far away would be too faint for even the best telescopes. In the 1980s, sensitive new CCD detectors became available. With these, astronomers at last had a chance of spotting small icy objects beyond Neptune. Americans David Jewitt and Jane Lu were among the astronomers who set about the difficult task. After 5 years of searching, in 1992, Jewitt and Lu discovered an object. Formally designated 1992 QB1, the first body to be found beyond Neptune since Pluto, and the first evidence that the Kuiper Belt was real. Cubanos and Plutinos. More than 1,000 Kuiper Belt objects are now known, and there are probably thousands more. They are designated as asteroids, but unlike most asteroids, KBOs are typically a mixture of rock and ices. The largest are several hundred miles across, and many of them have moons. 1992 QB1 is typical of the KBOs in the most densely populated middle part of the Kuiper Belt, about 45 Australian dollars from the Sun. These KBOs are sometimes called Cubanos. Closer in, at around 40 Australian dollars, the gravity of Neptune has thinned out the Kuiper Belt, leaving a family of objects called Plutinos in orbits that are unaffected by Neptune's gravity. Beyond the main Kuiper Belt lies a region called the scattered disk, which includes the large objects Eris and Sedna. It is now believed that this region is the source of short-period comets. In 2006, Eris was designated a dwarf planet along with Pluto. Since then, 2 more Cubanos, Makemake and Haumea, have been classed as dwarf planets, with many more KBOs listed as candidate dwarf planets. Scientists believe that these KBOs resemble the primitive bodies that formed the planets. The egg-shaped dwarf planet Haumea hangs in the sky above one of its 2 moons, Namaka. Haumea, discovered in 2004, is the 3rd largest dwarf planet. Gerard Kuiper. Gerard Kuiper was born in the Netherlands in 1905. At a time when few other astronomers were interested in the planets, Kuiper, working mostly at the University of Chicago, made many discoveries that changed the course of space science. He found that the Martian atmosphere was mostly carbon dioxide, that Saturn's rings comprised billions of chunks of ice, and that the Moon was covered in a fine rock dust. In 1949, Kuiper's idea that the planets were formed from a cloud of gas and dust that surrounded the young Sun changed scientists' view of the early solar system. In the 1960s, Kuiper helped identify landing sites on the Moon for the Apollo program and catalogued several binary stars. He died of a heart attack in 1973, at age 68. Since 1984, the Kuiper Prize has been awarded annually by the American Astronomical Society to recognize achievement in planetary science, a field of astronomy in which many consider Gerard Kuiper to have been the pioneer. See also, the Kuiper Belt, the Oort cloud studying Pluto. In context, key astronomers Michel Mayor, Didier Queloz. Before 1952, U.S. scientist Otto Struve proposes the radial velocity method to find exoplanets. 1992, the first such planet is found, orbiting a pulsar and not a main sequence star. After 2004, construction begins on the James Webb Space Telescope, which will be able to image exoplanets. 2005, the NICE model offers a new idea for the evolution of the solar system that places the giant planets closer to the Sun. 2014, the construction of the European Extremely Large Telescope begins. 2015, Kepler 442b, an Earth-sized rocky exoplanet around an orange dwarf, is discovered. In 1995, two Swiss astronomers, Michel Mayor and Didier Queloz, researching at the Observatoire de Haute-Provence near Marseille, found a planet orbiting 51 Pegasi, a sun-like star 60 light-years away in the constellation of Pegasus. This was the first confirmed observation of a true extrasolar planet, or exoplanet, a planet beyond the solar system. It was orbiting a main sequence star, and was therefore assumed to have formed by the same process as that which created the solar system. Mayor and Queloz named the new planet 51 Pegasi b, but it is unofficially known as Bellerophon after the hero who rode Pegasus, the winged horse of ancient Greek myth. Its discovery prompted a major hunt to find more exoplanets. Since 1995, several thousand exoplanets have been found, many in multiple star systems. Astronomers now estimate that there is an average of one planet around every star in the galaxy, although this is probably a very conservative figure. Some stars have no planets, but most, like the Sun, have several. The discovery of 51 Pegasi b marked the final milestone in a process that has forced astronomers to abandon any lingering notion that Earth occupies a privileged place in the universe. For more than 2,000 years, people have dreamed of finding other habitable worlds. Michel Mayor. Copernican Principle. In the 1950s, the Anglo-Austrian astronomer Hermann Bondi had described a new way for humans to think about themselves, which he called the Copernican Principle. According to Bondi, humankind could no longer regard itself as a unique phenomenon of central importance to the universe. On the contrary, humans should now understand that their existence is insignificant in the context of the universe. The principle is named after Nicholas Copernicus, who changed the way humankind saw itself by relegating Earth from the center of the solar system to one of several planets that orbited the Sun. By the late 20th century, successive discoveries had moved the solar system from the center of the universe to a quiet wing at the edge of a galaxy containing 200 billion other stars. The galaxy was not special either, simply one of at least 100 billion arranged in vast filaments that extended for hundreds of millions of light-years. Nevertheless, planet Earth and the solar system were still regarded as very special, since there was no evidence that any other stars had planets, let alone planets capable of supporting life. Since Mayer's and Queloz's discovery, however, this idea has also succumbed to the Copernican principle. We are getting much closer to seeing solar systems like our own. Didier Queloz. When a large Jupiter-like planet orbits its star, it exerts a gravitational pull on the star. Both star and planet revolve around a common center of gravity. The wobble in the star's orbit allows the planet to be detected. Wobbling light. Kulo and Mayer found 51 Pegasi B using a system called Doppler spectroscopy. Also known as the radial velocity or wobble method, Doppler spectroscopy can detect an exoplanet by its gravitational effects on its host star. The star's gravity is far greater than that of the planet, and this is what keeps the planet in orbit. However, the planet's gravity also has a small effect on the star, making it wobble back and forth as the planet moves around it. The effect is tiny. Jupiter changes the Sun's speed by about 12 miles s over a period of 11 years, while Earth's effect is only 0.1 miles s each year. In 1952, U.S. astronomer Otto Struve had suggested that this kind of star wobble could be detected as small fluctuations in a star's spectrum. As the star moved away from Earth, its emissions would be slightly redshifted from the norm. When it wobbled back again toward the observer, the light would be blue shifted. The theory was solid, but detecting the wobble required an ultra-sensitive detector. That detector was a spectrograph named LID developed by Mayer in 1993. LID was about 30 times more sensitive than any previous instrument. Even then, it was only capable of measuring velocity changes of 7 miles s, which meant it was limited to detecting planets about the size of Jupiter. The Kepler Observatory looked outward from the plane of the ecliptic, so that Earth, the Moon, and the Sun did not obscure the view. Improving the search. In 1998, an even more sensitive spectrograph, named Coralie, was installed at La Silla Observatory in Chile, which again was searching for planets using the radial velocity technique. In 2002, Michel Mayer began overseeing HARPS at the same site, using a spectrograph capable of detecting exoplanets about the size of Earth. The wobble method of detection was very slow, so new techniques of spotting exoplanets were developed. The most successful method was the transit method, which looked for periodic changes in the brightness of a star. These changes were very small and happened when a planet transited the star, passing between the star and the observer, and causing it to dim very slightly. The best place to look for exoplanets by the transit method was out in space, and so, in 2009, the Kepler Observatory, named after the man who first described planetary orbits, was launched to do just that. Staring at one place. Kepler was placed in a heliocentric orbit, trailing behind Earth as it circled the Sun. The craft was designed to keep its aperture firmly fixed on a single patch of space, called the Kepler field. This made up only about 0.25% of the whole sky, but the spacecraft could see 150,000 stars in that area. To find exoplanets, Kepler would have to concentrate on this single field of view for years on end. It was unable to see individual exoplanets, but could identify stars that were likely to have them. Kepler could only detect the transits of exoplanets with orbital paths that crossed the spacecraft's line of sight. Many exoplanets would be orbiting at the wrong angle for that. Those that were correctly oriented would only transit their star once every orbital period. So Kepler's method was better at finding planets that orbited close to their star, taking a few years and months to complete each revolution. We were not expecting to find a planet with a 4-day period. No one was expecting this. Michel Mayer. Candidate stars. By the start of 2013, Kepler had identified about 4,300 candidate stars that might have extrasolar planetary systems. Unfortunately, the guidance system used to keep Kepler locked on target then failed, bringing its planet hunt to an end about 3 years sooner than expected. However, the data it had collected was enough to keep researchers busy for years to come. Kepler's candidate stars could only be confirmed as planetary systems using radial velocity measurements from ground-based observatories, such as HARPS in Chile and the Keck telescope in Hawaii. So far, about a tenth of Kepler's candidate stars have proved to be false positives, but, after 3 years of analysis, the program had identified 1,284 exoplanets, with more than 3,000 stars left to examine. The statistics for the exoplanets in the Kepler field are striking. Most stars are part of a planetary system. This means that the number of planets in the universe is likely to exceed the number of stars. The amount of dimming during a transit gives an indication of how big an exoplanet might be, but the study of an exoplanet's size and characteristics is still in its early stages. The light reflected from a planet is about 10 billion times fainter than the star it orbits. Astronomers are waiting for the James Webb Space Telescope in 2018 and the European Extremely Large Telescope in 2024 to image this light directly and analyze the chemistry of exoplanets. Until then, they have to speculate using very little data: an approximate mass of the planet, its radius, the orbital distance, and the temperature of the star. This tells them what the planet is probably made of and allows them to conjecture what the surface conditions are likely to be. Red dwarfs with rocky planets could be ubiquitous in the universe. Phil Muirhead. The superjupiter, Kappa Andromedae b, shown here in an artist's render, has a mass of 13 times Jupiter's. It glows a reddish color, and may yet be reclassed as a brown dwarf. Hot and superjupiters. The exoplanets discovered so far have added a host of weird worlds to the neat family portrait that is the Sun's planetary system. For example, 51 Pegasi b was the first of many hot Jupiters. These have a mass similar to Jupiter's and a large size that shows that they are mostly made of gas. 51 Pegasi b is half as massive as Jupiter, but is slightly larger. This gas giant orbits its sun-like star every 4 days. That means it is much closer to its star than Mercury is to the Sun. Such proximity means it is tidally locked to the star. One side always faces the scorching stellar surface, and the other always faces away. Many hot Jupiters have been found. They have confounded scientists, who are trying to understand how gas planets can exist so close to a star without evaporating. Some exoplanets are dozens of times more massive than Jupiter, and are known as superjupiters. These superjupiter planets do not appear to grow in size as their mass increases. For instance, Corot 3b is a superjupiter that is 22 times as heavy as Jupiter but more or less the same size, due to its gravity holding its gaseous contents together. Astronomers have calculated that the density of Corot 3b is greater than that of gold and even osmium, the densest element on Earth. Kepler 10b in the Draco constellation is shown transiting its star in an artist's impression. Its extremely hot surface temperature and dizzying orbit mean life there is improbable. Brown dwarfs and rogues. When a superjupiter reaches 60 Jupiter masses, it is no longer regarded as a planet, but as a brown dwarf. A brown dwarf is essentially a failed star, a ball of gas that is too small to burn brightly through nuclear fusion. The brown dwarf and its star are seen as a binary star system, not a planetary one. Some superjupiters and small brown dwarfs have broken free of their star to become free-floating rogue planets. One, named MOA 2011 BLG 262, is thought to have a satellite, and could be the first exoplanet found with an exomoon. Another class of planet are called the super-Earths. These have a mass 10 times that of Earth but less than that of an ice giant like Neptune. Super-Earths are not rocky but made from gas and ice. Alternative names for them are mini-Neptunes or gas dwarfs. The size of the habitable zone depends on the size of the star. The red zone is too hot, while the blue zone is too cold. The habitable zone is closer to cooler stars than it is to hotter stars. The size of a planet, the shape of its orbit, and the speed of its rotation between night and day also affect its habitability. Living planets. Earth's solar system has terrestrial planets, of which Earth is the largest. So far, exoplanet searches have struggled to find many terrestrial planets, because they are generally small and beyond the sensitivity of the planet detectors. The first confirmed terrestrial exoplanet was Kepler 10b, which is 3 times the mass of Earth and is so close to its star that it orbits once an Earth day and has a surface temperature that would melt iron. Life seems highly unlikely there, but the hunt continues for rocky planets that might be more hospitable. Astrobiologists, scientists who search for alien life, focus on the particular conditions that all life needs. When choosing likely places to look, they assume that alien life forms will require liquid water and carbon-based chemicals, just like life on Earth. Living planets would also need an atmosphere to shield the surface from damaging cosmic rays and to act as a blanket that retains some of the planet's heat during the night. The region around a star where the temperatures would allow planets to have liquid water, carbon chemistry, and an atmosphere is known as its habitable zone, also called the Goldilocks zone, like baby bear's porridge in the fairy tale. Not too hot, not too cold. The size and locations of habitable zones depend on the activity of the host star. For example, if Earth were orbiting a K-type star, an orange dwarf that is considerably cooler than the Sun, it would need to orbit at about one-third its current distance to receive the same amount of warmth. Of the thousands of exoplanets that have been identified, only a tiny proportion are candidates orbiting in their star's habitable zones, with Earth-like conditions for life, rocky surface with liquid water. Typically, they are larger than Earth, and very few have good prospects for being Earth-like. If and when Earth-like planets are found, astrobiologists will look at the atmospheric chemistry for signs of life, such as the presence of elevated levels of oxygen, produced by photosynthesizing life forms. How life evolved from non-living material on Earth is still a mystery, but the study of Earth-like planets may throw light on that process. Even if life is found, it is likely that most extraterrestrial natural histories will not have moved beyond microorganisms. As every step toward evolving more complex life forms becomes ever more unlikely, so alien civilizations that match humankind's will be a lot less common. However, if only G-type stars, like the Sun, are counted, there are about 50 billion in the galaxy. It is estimated that 22% of them have an Earth-like planet in their habitable zones, which equals 11 billion possible Earths. Adding in other types of stars such as orange and red dwarfs, that number rises to 40 billion. Even if the probability of civilizations evolving is 1 in a billion, the chances are that humankind is not alone. If we keep working as well and we keep being as enthusiastic, the issue about life on other planets will be solved. Didier Queloz. Michel Mayor. Michel Mayor was born in Lausanne, Switzerland, and has spent most of his career working at the University of Geneva. His interest in exoplanets arose from his earlier study of the proper motion of stars in the Milky Way. To measure this motion more accurately, he developed a series of spectrographs, which eventually culminated in ELIDY. The ELIDY project with Didier Queloz was initially intended to search for brown dwarfs, objects that were bigger than planets, but not quite large enough to be stars. However, the system was sensitive enough to spot giant planets as well, and following their 1995 discovery, Mayer is currently the chief investigator at the HARPS program for the European Southern Observatory in Chile. His team has found about half of all the exoplanets discovered to date. In 2004, Mayer was awarded the Albert Einstein Medal. Key work. 1995 A Jupiter mass companion to a solar-type star. See also, the Copernican model radio telescopes studying distant stars looking farther into space. Kumar. In context. Key astronomer Donald York. Before 1929 Edwin Hubble proves that the universe is expanding. 1963 Martin Schmidt discovers quasi-stellar objects, or quasars, which turn out to be young galaxies. 1999 Saul Perlmutter, Brian Schmidt, and Adam Rees show that the expansion of the universe is increasing due to the mysterious effects of dark energy. After 2004 construction begins on the James Webb Space Telescope, which will use infrared to see the first stars that formed after the Big Bang. 2014 approval is given for the European Extremely Large Telescope, which will have a 128 feet segmented main mirror, making it the most sensitive optical telescope ever. Set up to produce a field guide to the heavens. The Sloan Digital Sky Survey began operating in 1998. The ambitious goal was to make a map of the universe on an immense scale, not just a survey of objects on a celestial sphere, but a three-dimensional model of a large portion of deep space. The project was initially headed by U.S. astronomer Donald York, but is now a collaboration between 300 astronomers from 25 institutions. SDSS uses an 8 feet 3 inches telescope at Apache Point, New Mexico. The telescope's wide-angle camera has digitized objects visible from the northern hemisphere. From the 500 million objects visible, the brightest 800,000 galaxies and 100,000 quasars were selected, and their sizes and positions in the sky accurately transposed as holes drilled into hundreds of aluminum disks. When fitted to the telescope, a disk blocks unwanted light, and feeds the light from each target galaxy into its own dedicated optical fiber and onto a spectroscope. From these accurate galactic spectra, the astronomers can figure out how far away each galaxy is. Data collection began in 2000 and is expected to continue until 2020. The information gathered so far has revealed galaxies in clusters and superclusters, and even galactic walls, immense structures containing millions of galaxies, forming a tangled cosmic web with vast voids in between. A cube section of the SDSS sky map shows the intricate distribution of matter in space. The tangles of light are interconnected galaxies. See also, beyond the Milky Way, quasars and black holes studying distant stars looking farther into space. In context, key astronomer Andrea Ghez. Before 1971, British astronomers Martin Rees and Donald Lynden Bell proposed that the radio waves emanating from Sagittarius A are produced by a black hole. After 2004, a smaller black hole is discovered in orbit around Sagittarius A. 2013, the Chandra X-ray Observatory sees a record-breaking X-ray flare from Sagittarius A, perhaps caused by an asteroid entering the black hole. 2016, the LIGO experiment makes the first detection of gravitational waves, capturing the moment when two black holes merged into one. In 1935, Carl Jansky found a source of radio waves named Sagittarius A at the center of the Milky Way. Hidden from light telescopes by cosmic dust, the radio waves emanated from several sources. In 1974, radio telescopes pinpointed the most intense source, named Sagittarius A. It was small and produced intense X-rays, suggesting that matter at the heart of the galaxy was being ripped apart by a gigantic black hole, emitting X-rays in the process. However, this remained hypothetical until Andrea Ghez, an astronomer at UCLA, used a method for observing stars through the dust using infrared. In 1980, Hawaii's Keck Observatory began measuring the speed of stars orbiting close to the galactic center. This data made it possible to calculate the mass of the invisible object inside SGRA. Gez's team found that the stars closest to SGRA were orbiting at a quarter of the speed of light. Such speed indicated an immense gravitational presence, a black hole 4 million times heavier than the Sun, which must have swallowed up stars and other black holes when the galaxy was young. An X-ray flare shoots from the black hole at the heart of the Milky Way. The discovery suggests all galaxies may have black holes at their hearts. See also, radio astronomy discovering black holes studying distant stars. In context, key astronomers Saul Perlmutter, Brian Schmidt, Adam Rees. Before 1917, Albert Einstein adds a cosmological constant to his field calculations to keep the universe static. 1927, Georges Lemaitre suggests that the universe could be dynamic, not static. 1928, Edwin Hubble finds evidence of cosmic expansion. 1948, Fred Hoyle, Hermann Bondi, and Thomas Gold proposed the steady-state theory of the expanding universe. After 2013, the Dark Energy Survey begins to map the universe. 2016, the Hubble Space Telescope shows that cosmic acceleration is 9% faster than originally measured. The Big Bang Theory has at its heart a simple idea: the universe started out very small and then expanded. In 1998, two teams of scientists discovered that the expansion of the universe is itself speeding up. This discovery revealed that what astronomers can directly detect makes up just 5% of the total mass and energy in the universe. Invisible dark matter makes up another 24%, while the rest is a mysterious phenomenon, known simply as dark energy. In 2011, three Americans, Saul Perlmutter, Brian Schmidt, and Adam Rees, won the Nobel Prize for Physics for this discovery. It's everywhere, really. It's between the galaxies. It is in this room. We believe that everywhere that you have space, empty space, you cannot avoid having some of this dark energy. Adam Rees. Expanding space. The year after Georges Lemaitre's paper hypothesized the Big Bang, Edwin Hubble found proof of the expanding universe when he showed that galaxies were moving away from Earth, and the ones that were farther away were moving faster. These were not simply objects blasting away from each other through space. This was space itself growing in size and moving the matter with it. The galaxies are not only moving away from Earth, they are expanding away from everywhere all at once. Better picture. Subsequent observations helped to tell the history of the expanding universe. The 1964 discovery of the cosmic microwave background, a cold glow left over from the Big Bang, showed that the universe has been expanding for approximately 13.8 billion years. Surveys of the large-scale structure of the universe have since revealed that billions of galaxies are clustered together around vast, empty voids. This structure corresponds to minute ripples in the CMB that show how observable matter, the stars and galaxies, emerged in anomalous regions in otherwise empty space. However, the future of the universe was uncertain. It was unknown whether it would expand forever or one day collapse under its own gravity. If you're puzzled by what dark energy is, you're in good company. Saul Perlmutter. Decelerating universe. Throughout the 20th century, cosmologists assumed that the rate of expansion was slowing down. Following a rapid initial expansion, gravity would start decelerating. It seemed there were two main possibilities. If the universe was heavy enough, its gravity would eventually slow the expansion to a stop and begin to pull matter back together in a cataclysmic big crunch, a kind of Big Bang in reverse. The second possibility was that the universe was too light to stop the expansion, which would therefore continue forever, gradually slowing down. This process would result in heat death, where the material of the universe had broken up, become infinitely dispersed, and ceased to interact in any way at all. A measurement of the deceleration of the universe's expansion would tell cosmologists which possible future the universe was heading for. By the mid-1990s, two programs were underway to measure the rate of expansion of the universe. The Supernova Cosmology Project was headed by Saul Perlmutter at Lawrence Berkeley National Laboratory, while Brian Schmidt, based at the Australian National University, led the High-Z Supernova Search Team. Adam Rees, of the Space Telescope Science Institute, was the lead author for the latter project. The project leaders considered merging, but had different ideas about how to proceed, and so opted instead for a healthy rivalry. Both projects were using a discovery made by the Callan-Celodo Supernova Survey, carried out in Chile between 1989 and 1995. The survey found that Type 1a supernovae could be used as standard candles, or objects that can be used to measure distances across space. A standard candle is an object of known brightness, and so its apparent magnitude shows how far away it is. A Type 1a supernova is a little different from a standard supernova, which forms when large stars run out of fuel and explode. A Type 1a forms in a binary star system, in which a pair of stars orbit each other. One is a giant star, the other is a white dwarf. The white dwarf's gravitational pull hauls stellar material over from the giant. The material accretes on the surface of the white dwarf until it has grown to 1.38 solar masses. At this point, the temperature and pressure are such that a runaway nuclear fusion explosion ignites the star, creating an object billions of times brighter than the Sun. The Chandra X-ray Observatory took this image of the remnant of Type 1a supernova SN 1572 in Cassiopeia. It is also known as Tycho's nova, as it was observed by Tycho Brahe. Distance and motion. Both surveys used the Cerro Tololo Inter-American Observatory in Chile to find Type 1a supernovae. The plan was not simply to plot the positions of the supernovae. They used the Keck telescope in Hawaii to take spectra of each explosion, giving its redshift. The brightness, or magnitude, of each star gave the distance, often billions of light years, while its redshift indicated its speed relative to Earth, caused by the expansion of the universe. The teams were aiming to measure the rate at which the expansion was changing. The rate of expansion, as indicated by more distant objects, was expected to be tailing off. Exactly how fast it was doing this would show if the universe was heavy or light. However, when the teams looked beyond about 5 billion light-years, meaning that they were looking 5 billion years into the past, they found that the opposite was happening. The expansion of the universe was not slowing down but speeding up. A computer simulation shows a white dwarf star exploding in a Type 1a supernova. A flame bubble forms inside the star, rises above the surface, and envelopes the star. Dark energy. This result was first thought to be an error, but successive checks showed it was not, and both teams found the same thing. In 1998, Perlmutter and Schmidt went public with their findings. The results shook the scientific world. Using Einstein's field equations for general relativity, Adam Rees had found that the results appeared to give the universe a negative mass. In other words, it appeared that a kind of anti-gravity force was pushing matter apart. This source of energy was named dark energy, because it was a complete mystery. In 2016, new observations were used to calculate a more accurate, and slightly faster, figure for the acceleration of the universe's expansion. If dark energy continues to push the universe apart, it will disperse the galaxies so that eventually they would all be too far away to be seen from Earth. Eventually, it may scatter the stars within the Milky Way until the sky goes dark. The Sun and the planets in the solar system would be pulled apart, and finally the particles and atoms will also be scattered, resulting in a form of heat death dubbed the Big Rip. This discovery has led us to believe that there is some unknown form of energy that is ripping the universe apart. Brian Schmidt. Reviving Einstein's mistake. Dark energy may indicate that the universe is not as homogeneous as cosmologists think it is, and that the apparent acceleration seen is due to the fact that it is inside a region with less matter in it than elsewhere. It may also be showing that Einstein's theory of gravity is incorrect on the largest scales. On the other hand, dark energy might also be explained by a mathematical device Einstein created in 1917 called the cosmological constant. Einstein used this as a value that would counteract the pull of gravity and make the universe a static, unchanging place. However, when Lemaitre used Einstein's own equations to show that the universe could only be dynamic, expanding or contracting, Einstein dropped the constant from his theories, calling it a mistake. The value of Einstein's cosmological constant is set to match the energy contained in a vacuum, in empty space. This was assumed to be zero. However, according to quantum theory, even a vacuum contains virtual particles, which exist for a Planck time and then disappear again. Dark energy may match this idea, a form of energy arising from these virtual particles, which creates a negative pressure that pulls space apart, and represents a non-zero value for the cosmological constant. The expansion was not always accelerating. There was a time when gravity and other forces pulled matter together, and was more powerful than dark energy. However, once the universe became big and empty enough, the effects of dark energy appear to have become dominant. It may be that a different force takes over in the future, or dark energy's effects may continue to grow. One suggestion is that a big rip would be so powerful that dark energy will tear apart space-time itself, creating a singularity, the next Big Bang. Dark Energy Survey. In 2013, the Dark Energy Survey began a 5-year project to map the expansion of the universe in detail. The project uses the Dark Energy Camera at Cerro Tololo Inter-American Observatory, Chile. The camera has one of the widest fields of view in the world. In addition to searching for Type 1a supernovae, the project is looking for baryon acoustic oscillations. These are regular ripples in the distribution of normal matter about 490 million light-years apart, which can be used as a standard ruler to show up cosmic expansion. See also, the theory of relativity spiral galaxies, the birth of the universe beyond the Milky Way, searching for the Big Bang dark matter redshift surveys. In context. Key development. James Webb Space Telescope. Before 1935, Karl Jansky shows that radiation other than light can be used to view the universe. 1946, Lyman Spitzer Jr. suggests placing telescopes in space to avoid atmospheric interference. 1998, the Sloan Digital Sky Survey begins to make a 3D map of the galaxies. After 2003, the Spitzer Space Telescope, an infrared observatory, is launched. 2014, the European Extremely Large Telescope project is approved, with a primary mirror 39 m in diameter. 2016, LIGO announces the discovery of gravitational waves, suggesting a possible means for looking even farther than the JWST. The James Webb Space Telescope is designed to be the most powerful astronomical tool in space, able to see farther than even the Hubble Space Telescope. Named in 2002 after the NASA director who oversaw the Apollo program, the JWST is an infrared telescope equipped with a 21 feet wide gold-plated mirror. This will allow it to see more than 13.5 billion light-years into the distance, to the time when the universe's first stars were forming. Conceived in 1995 as the successor to Hubble, the JWST has had a long road to completion, encountering multiple technical hurdles. When launched in 2018, it will take up a tight orbit around L2, a location 1 million miles beyond Earth's orbit, away from the Sun. L2 is a place in space where the gravity of the Sun and Earth work together to pull an orbiting object around the Sun at the same rate as Earth, making one orbit every year. This means the JWST will be largely in the shadow of Earth, blocking out any heat pollution from the Sun and allowing the telescope to detect very faint infrared sources in deep space. NASA claims that the telescope could detect the heat of a bumblebee on the Moon. An artist's impression of the JWST in space shows the layered stack of the Sun shield unfolded beneath the telescope. The beryllium mirror is coated in gold for optimal reflection. Heat seeker. The JWST's vast primary mirror is 7 times the area of Hubble's and, instead of polished glass, the mirror contains 18 hexagonal units made from beryllium for maximum reflection. The 270 SQ-FT mirror is too large to be launched flat, so it is designed to unfold once in orbit. To pick up the faint heat signatures of the most distant stars, the telescope's detectors must always be extremely cold, never more than 370 degrees Fahrenheit. To accomplish this, the JWST has a heat shield the size of a tennis court. Again, this is folded away for launch. The shield is made from 5 layers of shiny plastic that reflect most of the light and heat. Any heat that penetrates the top layer is then radiated sideways by successive inner layers so that almost nothing reaches the telescope itself. First light. The light waves from the first stars to form have been stretched as they shine through the expanding universe, changing them from visible light to infrared, so they are a prime target of observation for the JWST. At the same time, this ultra-sensitive eye on the infrared sky has 3 other main goals. It will investigate how galaxies have been built over billions of years, study the birth of stars and planets, and provide data about extrasolar planets. NASA hopes that the telescope will be in operation for at least 10 years. JSWT will not be exactly at the L2 point, but will circle around it in a halo orbit. Lagrange points are positions in the orbit of 2 large bodies where a smaller object can keep a stable position relative to those 2 large bodies. There are 5L points in the orbital plane of Earth and the Sun. See also, Radio Astronomy Space Telescopes, a digital view of the sky's gravitational waves Lagrange. In context. Key development ESA, Rosetta. Before 1986, the Halley Armada of 8 spacecraft, led by ESA's Giotto, make observations of Halley's Comet. 2005, the Deep Impact mission fires a probe at Comet Tempel 1 to create a crater in the surface, and analyzes what is underneath. 2006, the Stardust mission collects a capsule of cometary dust from the tail of Comet Wild 2 and returns to Earth. After 2015, New Horizons flies by Pluto and begins an exploration of the Kuiper Belt. 2016, NASA's OSIRIS-RX spacecraft is launched with a mission to collect and return a sample from the asteroid 101955 Bennu. By studying comets, astronomers hope to shed new light on various questions about the early solar system, the formation of Earth, and even the origins of life. Earth is the only planet known to have a surface ocean of liquid water. The origin of this water is one of the enduring mysteries of Earth's science. A leading theory is that the hot, young planet sweated out the water from its rocks, releasing water vapor into the atmosphere. Once the planet had cooled sufficiently, this vapor condensed and fell as a deluge of rain that filled the oceans. Another theory argues that at least some of the water arrived from space, specifically in the hundreds of thousands of icy comets that rained down on Earth during the first half-billion years of its existence, and vaporized on impact. A flyby of Halley's Comet in 1986 by a flotilla of spacecraft led by ESA's Giotto got the first close-up look at a comet's core, or nucleus. The Halley encounter provided conclusive proof that comets are largely made from water ice mixed with organic dust and chunks of rock. This revived the theory that this is where Earth's oceans came from. One theory concerning the origin of life was that the complex chemical building blocks necessary for life, such as amino acids and nucleic acids, arrived on Earth from space. Perhaps these organic compounds were also delivered to Earth by comets. The only way to find out was to send a spacecraft to meet up with a comet and land on its surface. In 2004, the ESA-led Rosetta mission blasted off on a 10-year journey to do just that. Giotto ignited the planetary science community in Europe. Gerhard Schwemm, Giotto project scientist. Fresh target. Rosetta's intended target was Comet 67P Churyumov-Gerasimenko, or 67P for short. In 1959, this comet had been captured by the gravity of Jupiter, which had pulled it into a shorter 6-year orbit of the Sun. Before that, 67P had been circling the Sun much farther away. This excited the Rosetta scientists because the tail of a comet, its most familiar feature, is caused by solar radiation heating the surface of the nucleus, which creates streams of dust, gas, and plasma hundreds of millions of miles long. The material in the tail is lost from the comet forever. 67P had only been close to the Sun a handful of times in its existence. That meant it was still fresh, with its primordial composition intact. In 2005, the Deep Impact impactor collided with Comet Tempel 1, releasing debris from the comet's interior. Analysis showed the comet to be less icy than expected. All aboard. Rosetta was launched by an Ariane 5 rocket from ESA's Space Center in French Guiana. The spacecraft weighed just under 3 tons, with a central body about as large as a small van. A folded solar array unfurled to provide 690 square feet of photovoltaic cells, which would power the craft throughout the mission. Most of Rosetta's instruments were designed to study the comet while in orbit. They included various spectroscopes and microwave radars for studying the composition of the comet's surface and the dust and gases that would be released when 67P neared the Sun and began to heat up. One of the most important instruments on board was CONSERT, which would blast a beam of radio waves through the comet to find out what lay inside. CONSERT would operate with the help of the lander Philae. Once on the surface, Philae would pick up signals from CONSERT, sent out while Rosetta was orbiting on the far side. Philae was equipped with solar panels and rechargeable batteries and was designed to work on the comet's surface in order to analyze its chemistry. Both the names Rosetta and Philae referred to ancient Egyptian artifacts. The Rosetta Stone has a carved inscription in 3 languages: hieroglyphs, Demotic Egyptian, and Ancient Greek. In the early 19th century, it allowed scholars to decipher the hieroglyphic writing system, thus unlocking the meaning of many ancient Egyptian writings. Philae refers to an obelisk with multiple inscriptions that was used in a similar way. Comets are remnants left over from the formation of the solar system, so these names were chosen because the Rosetta and Philae missions at Comet 67P were intended as a way to unlock new knowledge of the primordial material that formed the planets. An artist's impression shows Rosetta releasing the Philae lander above Comet 67P. The lander bounced on landing, flying up from one lobe of the comet to land again on the other. "We didn't just land once, maybe we landed twice." Stefan Ulemek, Philae landing manager. Comet cruise. Rosetta took a circuitous route to the comet, using 3 flybys of Earth and 1 of Mars to boost speed through gravity assists. This process took 5 years, after which Rosetta had enough speed to fly through the asteroid belt and out beyond the orbit of Jupiter. There, it began to swing back around, and was soon bearing down on 67P at great speed. For the journey to deep space, Rosetta had been powered down to save energy, but it powered back up and contacted Earth on schedule as it neared the comet in August 2014. Rosetta's controllers then began a series of thruster burns to make Rosetta zigzag through space and slow from 2,540 foot s to 26 foot s. On September 10, the spacecraft went into orbit around 67P, offering the first look at the target world. Bumpy landing. Comet 67P is about 2.5 miles long and turned out to be more irregular in shape than expected. From some viewpoints, the comet looks like a vast rubber duck, with its 2 lobes, one larger than the other, connected by a narrow neck. The surface was riddled with boulder fields and ridges, and the Rosetta team struggled to find a clear location to set down the Philae lander. A landing zone on the head of the comet was selected, and at 8:35 Greenwich Mean Time on November 12, 2014, Philae was released from Rosetta. It took almost 8 hours to confirm that Philae was on the surface, much longer than expected. The lander was designed to touch down at a slow speed, slower than an object dropped from shoulder height on Earth, and attach itself to the ground using harpoons fired from the tips of its legs. However, something had gone wrong. It is thought that the lander landed awkwardly and hit a boulder, and the very low gravity of the comet meant Philae bounced right off again. It was later calculated that Philae bounced up about 3,000 feet from the surface before falling back again, tumbling to a resting place on the edge of the target landing zone. Unfortunately, the lander ended up in the shadow of a cliff and appeared to be at an angle. Without sunlight to recharge its batteries, Philae had only about 48 hours of power to perform its primary science missions, returning data on the chemical composition of the dust and ice, and performing scans with the CONSERT instrument on Rosetta. A last-ditch plan to push the lander out into the sunlight using the harpoons failed, and Philae shut down into safe mode. Rosetta captured this image of Comet 67P Churyumov-Gerasimenko on July 14, 2015, from a distance of 96 miles. As the comet neared its closest point to the Sun. Approaching the Sun. Despite this setback, the perilous Philae landing was deemed a success. The hope was that Philae's shaded location would become sunnier as the comet approached the Sun. The comet would reach its perihelion, or closest point, in August 2015. On the approach, Comet 67P began to heat up and its surface erupted with jets of dust and plasma. Rosetta was sent on a complex orbital path so that it could fly low over the comet and pass through the denser regions of the coma, or cloud of material, that was forming around 67P. Its path also took it farther out, providing a more complete picture of the ways in which the comet was changing as it entered the warmer part of the solar system. In mid-June 2015, Philae received enough sunlight to wake up and began intermittent communication with Rosetta, allowing further concerted scans. In early July, however, it fell silent again. Fortunately, it was spotted by the OSIRIS camera on September 2, 2016, as it approached within 1.7 miles of the comet. Knowing Philae's precise landing spot allows scientists to place the information it sent back a year earlier into context. After Comet 67P passed perihelion in August 2015, the solar power available to Rosetta fell rapidly. In September 2016, Rosetta was instructed to get slowly nearer to the comet. It ended its mission on September 30 by making a controlled crash landing, returning data right up to the moment of impact. "We are on the surface of the comet. Whatever we do has never been done before. The data we get there is unique." Matt Taylor, Rosetta Project scientist. Rosetta received gravity assists from both Earth and Mars en route to Comet 67P. As it swung around the planets, their gravitational fields threw the spacecraft forward at greatly increased speed. Alien water. The amount of deuterium found in 67P's water is much greater than in the water found on Earth, evidence against the idea that Earth's water is of extraterrestrial origin. The mission has found many carbon-based compounds, but only one amino acid. And no nucleic acids have been detected in the data. Rosetta's results will allow astronomers to better understand comets and whether 67P is a typical body. Combined with discoveries from the Kuiper Belt, this is hoped to reveal what the solar system was made of as the Sun formed. On July 16, 2016, Rosetta was just 8 miles from the center of Comet 67P. This image covers an area about 1,500 feet across. It shows a dust-covered rocky surface. See also, the Oort cloud, the composition of comets investigating craters exploring beyond Neptune studying Pluto. In context, key astronomers Rodney Gomez, Hel Levison, Alessandro Morbidelli, Cleomenes Tsiganis before 1943. Kenneth Edgeworth suggests that Pluto is just one of many objects in the outer solar system. 1950. Jan Oort suggests that long-period comets come from a distant cloud surrounding the solar system. 1951. Gerard Kuiper proposes that a comet belt existed beyond Pluto in the early stages of the solar system. 1993. American planetary scientist Renan Malhotra suggests that planet migration took place in the solar system. 1998. The Kuiper belt is confirmed to exist. After 2015 spacecraft New Horizons reaches the Kuiper belt. By the start of the 21st century, the solar system was known to contain many kinds of object. In addition to the planets and the asteroid belt, there were comet-like bodies called centaurs located in between the giant planets, Trojan asteroids sharing the orbits of many planets, and the outer Kuiper belt had also just been discovered. Surrounding all these bodies was a distant sphere of comet material, called the Oort cloud. It was difficult to explain how a system like this had evolved from a protosolar cloud of dust and gas. Evidence from extrasolar systems showed that giant planets were often much closer to their star than was previously thought possible. It was at least feasible, therefore, that the giant planets of Earth's solar system had formed closer to the Sun. Planetary migration. In 2005, astronomers in Nice, France, used computer simulations to develop a theory to explain the evolution of the solar system. This is now known as the Nice model. They suggested that the solar system's 3 outer planets, Saturn, Uranus, and Neptune, were once much closer to the Sun than they are now. Jupiter was slightly farther away than it is now at 5.5 astronomical units, but Neptune was much closer, at 17 Australian dollars. From Neptune's orbit, a vast disk of smaller objects called planetesimals spread to 35 Australian dollars. The giant planets pulled these planetesimals inward and, in return, Saturn, Uranus, and Neptune started slowly edging farther away from the Sun. Planetesimals encountering Jupiter's powerful gravity were fired out to the edge of the solar system to form the Oort cloud, and this had the effect of shifting Jupiter inward. The NICE model changed the whole community's perspective on how the planets formed and how they moved in these violent events. Hal Levison. Resonant orbit. Eventually, Saturn shifted to a resonant 1:2 orbit with Jupiter, which meant that Saturn orbited once for every 2 orbits of Jupiter. The gravitational effects of this resonant orbit swung Saturn, then Uranus and Neptune into more eccentric orbits. The ice giants swept through the remaining planetesimal disk, scattering most of it, to create what is known as the Late Heavy Bombardment, which occurred about 4 billion years ago. Tens of thousands of meteorites were punched from the outer disk and rained down on the inner planets. Much of the planetesimal disk became the Kuiper belt, tied to Neptune's orbit at $40. Some planetesimals were captured by the planets to become moons, others filled stable orbits as Trojans, and some may have entered the asteroid belt. Planetesimals were also scattered farther out, including the dwarf planets Sedna and Eris, discovered in 2003 and 2005. The NICE model works well for many starting scenarios for the solar system. There is even one in which Uranus is the outermost planet, only to swap places with Neptune 3.5 billion years ago. During the late heavy bombardment, the Moon would have glowed as it was struck by meteorites. Most of the early Earth's surface was volcanic. Rodney Gomes. Brazilian scientist Rodney Gomes is a member of the NICE model quartet of scientists that came to prominence in 2005. It also includes American Hal Levison, Italian Alessandro Morbidelli, and Greek Kleomenes Tsiganis. Gomes, who has worked at Brazil's National Observatory in Rio de Janeiro since the 1980s, is a leading expert in the gravitational modeling of the solar system, and has applied techniques similar to those used in building the NICE model to understand the motion of several Kuiper belt objects that appear to be following unusual orbits. In 2012, he shook up the accepted view of the solar system yet again. Gomes proposes that a Neptune-sized planet is orbiting 140 billion miles from Earth, and that this mysterious planet is distorting the orbits of the KBOs. The search is now on to locate this Planet X. See also, the discovery of Ceres, the Kuiper belt, the Oort cloud, investigating craters exploring beyond Neptune. In context. Key astronomer Alan Stern. Before 1930, Clyde Tombaugh discovers Pluto, which is named as the 9th planet. 1992, Pluto is found to be one of many Kuiper belt objects orbiting the Sun beyond Neptune. 2005, another Pluto-sized object is found beyond the orbit of Neptune. It is called Eris. After 2006, Pluto, Eris, and several other objects are reclassified as dwarf planets. 2016, a skewing of the orbits of Kuiper belt objects suggests that there is a Neptune-sized planet much farther out in space, orbiting the Sun every 15,000 years. The search is now on for this object. In January 2006, NASA's New Horizons spacecraft lifted off from Cape Canaveral on a voyage to the planet Pluto and beyond. The moment was testament to the perseverance of the principal investigator for New Horizons, Alan Stern. Planetary demotion. At the time, nobody knew what Pluto actually looked like. It was small and far away on the inner rim of the Kuiper belt, and even the mighty Hubble Space Telescope could only render it as a pixelated ball of light and dark patches. Plans to explore Pluto close-up were thwarted during the 1990s as NASA budgets were squeezed. By 2000, the plans had been shelved, but Stern made the case for sending a mission to Pluto, the smallest, most distant planet, which had been discovered by U.S. astronomer Clyde Tombaugh in 1930. In 2003, Stern's New Horizons proposal was given the green light, and the 2006 launch set the spacecraft on a 9-year flight to Pluto. It occurred not a moment too soon. In August 2006, prompted by the discovery of a possible 10th planet beyond the orbit of Pluto, the General Assembly of the International Astronomical Union gathered in Prague to discuss issues raised by the new discovery. The first question was whether it was a planet at all. The IU agreed that the new body, to be named Eris, was not a planet. Its gravity was too weak to clear other bodies from its orbit. The planets from Mercury to Neptune are big enough to do this, but the bodies of the asteroid belt manifestly are not, and nor was Pluto. However, Pluto and Eris were not like most asteroids. They were massive enough to be spherical rather than irregular chunks of rock and ice. So the IU created a new class of object, that of dwarf planet. Pluto, Eris, and several large Kuiper belt objects were given dwarf planet status, as was Ceres, the largest body in the asteroid belt. For most of these objects, this was a promotion in the hierarchy of the solar system, but not for Pluto. If Pluto had been declassified as a planet prior to New Horizons' launch, it is uncertain whether the mission would have happened. Just as a chihuahua is still a dog, these ice dwarfs are still planetary bodies. Alan Stern. Long journey. Although Pluto's orbit does bring it closer to the Sun than Neptune for some of its 248-year revolution around the Sun, the New Horizons probe had the longest journey to the most distant target in the history of space exploration, $30 or 2.7 billion miles from Earth. To achieve this, the spacecraft was given the fastest launch ever, blasting off with an escape velocity of 36,373 miles per hour. A year after launch, the spacecraft reached Jupiter. In addition to making some observations of the Jovian system, New Horizons used Jupiter's gravity to gain a 20% speed boost. This cut the flight time to Pluto from over 12 years to 9.5 years. Instruments on board. The precision of the trajectory from Jupiter was crucial to the success of New Horizons. If it was just slightly off, the craft would miss Pluto altogether. The main observation window was about 12 hours long, after which New Horizons would be leaving Pluto behind. It takes radio signals from Pluto 4.5 hours to reach Earth, plus the same again to send a return message. Therefore, it would take at least 9 hours to make even tiny course corrections, by which time the primary mission would be almost over. New Horizons carried 7 instruments. They included 2 imaging spectrometers, built to work together and named after the characters in the 1950s US sitcom The Honeymooners. Ralph was the visible and infrared spectrometer used to make maps of Pluto's surface, while Alice was sensitive to ultraviolet and was tasked with studying Pluto's thin atmosphere. Rex would take the temperature of Pluto and its moons. Lori, a telescopic camera, would produce the highest resolution pictures of the Pluto system. Swap would, as the name suggests, observe Pluto's interaction with the solar wind, while Pepsi detected the plasma given off by Pluto. This would help in understanding the way the dwarf planet's atmosphere is formed by sublimation from the icy surface during Pluto's summer, as it nears the Sun. Finally, the SDC was an instrument operated by university students throughout the mission. This experiment was renamed VBSDC for Venetia Burney, the British girl who had proposed the name Pluto. New Horizons scientific instruments were switched off to conserve power for most of its 10-year journey, but they were powered up for 1 month a year so that checks could be made. Destination reached. New Horizons began its approach in January 2015. One of the first things it did was to make an accurate measurement of Pluto's size. This had always been a tricky problem to solve. When it was first discovered, it was estimated that Pluto was 7 times the size of Earth. By 1978, it was clear that Pluto was smaller than Earth's moon. However, it also had a huge satellite, named Charon, which was about a third of the size of Pluto, and the 2 bodies moved around each other as a binary system. At launch, planners also took into account 2 more tiny moons, Nix and Hydra, but by 2012, with New Horizons already well on the way, it was found that there were two more, Kerberos and Styx, which could potentially disrupt the mission. It used to be that Pluto was a misfit. Now it turns out that Earth is the misfit. Most planets in the solar system look like Pluto, and not like the terrestrial planets. Alan Stern. Measuring Pluto. In the end, these worries were misplaced, and Laurie was able to obtain a measurement for all of these bodies. Pluto is 1,470 miles wide, meaning that it is larger than Eris. On July 14, 2015, New Horizons flew 7,750 miles above Pluto, its closest approach. Its instruments were collecting huge quantities of data to be fed back to Earth. The close-up view of Pluto showed it to be a world of pale ice plains and dark highlands. The ice is largely frozen nitrogen, which makes Pluto a very bright object for its size. The highlands are also ice. The ice is thrust into lumpy peaks that tower 2 miles above the plains. Quite how such huge features arose on such a cold and small body is one of the mysteries of the New Horizons mission. In addition, crater-like structures have been identified as possible ice volcanoes. This view from New Horizons zooms in on the southeastern portion of Pluto's Great Ice Plains, where the plains border rugged, dark highlands. Naming the landmarks. Pluto's surface features have been given unofficial names by NASA scientists. Cthulhu Regio is a large whale-shaped dark patch in the southern hemisphere. Other regions are named after past missions, Voyager, Venera, and Pioneer. Two main mountain ranges have been imaged clearly, Norgay Montes and Hillary Montes, named after the first two climbers to reach the summit of Mount Everest. However, the central feature of New Horizons' partial map of Pluto is Tomboa Regio, a heart-shaped plain. Half of this area is made up of Sputnik Planitia, a vast ice flow riddled with cracks and troughs, but with no craters, which suggests it is a young feature that is carving out new surface features like glaciers on Earth. Now past Pluto, the craft is on course to meet up with other KBOs. Its nuclear power source should last until around 2030, and the mission should make many more discoveries. Alan Stern. Born Sol Alan Stern in New Orleans, Louisiana, in 1957, Stern's fascination with Pluto began in 1989 when he worked with the Voyager program. While he was there, Stern witnessed the final encounter of Voyager 2 as it flew past Neptune and its moon Triton. Triton appeared as a ball of ice, and looked very much like the Pluto Stern and other scientists had imagined. In the 1990s, Stern trained as a space shuttle payload specialist, but he never got the chance to fly into space. Instead, he returned to the study of Pluto, the Kuiper Belt, and the Oort cloud. In addition to leading the New Horizons mission as principal investigator, Stern is active in developing new instruments for space exploration and more cost-effective ways of putting astronauts into orbit. Key work. 2005 Pluto and Charon, ice worlds on the ragged edge of the solar system. See also, the Oort cloud, the composition of comets exploring the solar system, exploring beyond Neptune. In context. Key organization NASA, Mars exploration. Before 1970, the Soviets' Lunokhod 1 becomes the first vehicle to be used on another body when it touches down on the Moon. 1971, the lunar roving vehicle is driven on the Moon for the first time during NASA's Apollo 15 mission. 1977, NASA's Sojourner is the first rover to reach Mars. After 2014, Opportunity breaks the distance record for a rover on an extraterrestrial body. 2020, the NASA Mars 2020 rover is set to be launched as a replacement for Curiosity. 2020-21, the ExoMars rover is due to be deployed by the European Space Agency in Oxia Planum, a depression filled with clay-bearing rocks. In August 2012, the Mars Science Laboratory rover, better known as Curiosity, landed on Mars. This 2,000 pounds wheeled vehicle, which is still roaming the Martian surface, is a mobile laboratory equipped to conduct geological experiments aimed at figuring out the natural history of the red planet. It is the latest robot explorer to reach Mars, and the largest and most advanced in a long line of rovers sent to explore other worlds. Mars has been flown by, orbited, smacked into, radar examined, and rocketed onto, as well as bounced upon, rolled over, shoveled, drilled into, baked, and even blasted. Still to come, Mars being stepped on. Buzz Aldrin. Wanderers. The potential of rovers in space was clear as far back as 1971, when Apollo 15 carried a four-wheel lunar roving vehicle to the Moon. This agile two-seater widened the scope of lunar exploration for the